Hello and good day everyone. So today our group will be doing a video presentation for our project, the Hospital Patient Record System. My group member consists of me, Hafifadlin bin Nurmain, Muhammad Hakim and Muhammad Azim. The Hospital Patient Record System simulates a real-world multi-threaded environment where multiple nurses and doctors, the reader threads, can access a shared patient record simultaneously. While updating doctors, writer threads must obtain exclusive access before modifying the record. Built in C using POSIX threads on Ubuntu 22.04, the system uses a mutex RC underscore mutex to protect the reader counter, a binary semaphore WRT to enforce exclusive write access, and a fair FIFO queue as an advanced feature to prevent writer starvation. All thread activity is recorded to a timestamp hospital audit log, and the system was validated through 6 structured test cases, all of which passed successfully. Alright, so there are 4 problem statements. The first one is multiple nurses and doctors accessing the same patient record simultaneously, causing race condition and data corruption. Second one is the standard first reader writer solution. Prioritize readers. If nurses continuously arrive, updating doctors are permanently denied access, causing writer starvation. The third one is updating the shared reader count and accessing patient record.txt requires strict serialization to prevent inconsistent or partial reads. And lastly, the concurrent writers to hospital audit log.txt by multiple threads cause garbled and interleaved audit entries, violating hospital compliance requirements.
Good evening, everyone. My name is Muhammad Azim bin Romidi, number metric BI2411011. Moving on to our project goals, our primary objective is to design a robust concurrent system tailored for a hospital environment where patient record must be accessed safely and efficiently. As shown, we have broken this down into 4 core milestones. First, we apply mutex and binary semaphore synchronization to prevent rest condition and ensure exclusive write access to patient records. Second, we implement a fair fee4q as our advanced feature. In typical readers writer scenarios, writer can easily suffer from starvation if a continuous stream of readers hold the logs. This ticket-based FIFO queue ensures threads are served in the exact order of arrival, eliminating starvation entirely. Third, the core behavior of our system allows multiple nurses and doctors to read patient records simultaneously to keep up with fast-paced hospital demand while ensuring updating doctor get completely isolated, exclusive access. The fourth one, to maintain accountability, we built a thread-safe logging system. Every single thread action is instantly recorded with a precise timestamp to a central file named hospital underscore audit underscore log.txt, future audit and analysis. Now let's take a look at how these goals translate into our actual concrete system architecture. Looking at the flowchart and breakdown, our architecture is designed as a multi-layer synchronization pipeline. The fairness layer, counter layer, resource gatekeeper, and logging layer. So the fairness layer at the very top, when reader and writers arrive, they must interface with a queue mutex. This mutex protect our FIFO ticket variable, specifically next ticket and now serving. This is the mechanism that ensures threads are strictly ordered by arrival time before they even attempt to touch the data. Next, the counter layer below that, we have an RC mutex. This is dedicated solely by to ensure atomic updates to the reader count. By protecting this counter, we prevent rest conditions when multiple reading threads try to increment or decrement the active reader totally at the same time. Next, we have the resource gatekeeper, the actual access to the share patient file, patient underscore record.txt, is guarded by a binary semaphore named WRT. This ensures the ultimate reader writer rule. Either one single writer has exclusive access, or a group of multiple reader can read concurrently, but never both at the same time. The logging layer, the last one, at the base of our architecture, we isolate file append writes using a dedicated log mutex. This guarantees that when threads concurrently log their operation, the entries don't overlap or corrupt, ensuring every event is cleanly timestamped and recorded into hospital underscore audit underscore log.txt. That's all from me.
Moving on to the next slide. Before that, my name is Muhammad Hakim bin Muhammad Hanif. Matric number BI24110409. So, in our implementation, every thread, whether a reading nurse or an updating doctor, must first pass through the fair FIFO queue, where it takes a numbered tickets and wait until now serving matches before proceeding. This guarantees strict arrival order processing and completely eliminates writer starvation. For reader threads, the first nurse to arrive acquires the right semaphore (WRT), which blocks all writers from entering. Subsequent readers increment reader count safely under RC mutex and read concurrently alongside each other. When the last reader finishes and reader count drops to zero, it releases write (WRT), signaling that a writer may now proceed. For writer threads, after clearing the queue, the updating doctor acquires WRT exclusively, write exclusively, meaning no reader or other writer can be active at the same time. And finally, every significant event throughout this entire flow is captured by write underscore log, which timestamps it and appends it to hospital audit log.txt, protected by its own log mutex to ensure no two threads ever produce interleave or corrupted log entries. Moving on to the next slide, testing and empirical result. So for our testing, we compiled the program and ran it in Ubuntu using VirtualBox. On the left screen, you can see Dr. 1 wrote to the patient record first, then released the log before Dr. 2 could write. This shows that only one doctor can update the record at a time. After both doctors finish, all five nurses read the record at the same time. You can see the active readers count going up from 1 to 5, then back down to 0. This proves that multiple nurses can read together without any problem. On the top, we ran cat patient underscore record dot txt, and it shows doctors two final diagnosis: type 2 diabetes, metformin 500 milligram, which means no data was corrupted or overwritten wrongly. On the right screen is our audit log. Every action by every thread was recorded with a timestamp. Doctors came first, then nurses, then the system end, in the correct order, with nothing missing or mixed up. All six test cases passed successfully. That's all for me. Thank you. For group contribution metrics, Mohammad Azim designed the core synchronization models, structural flow diagrams, and slide layout. Hafi programmed the POSIX thread routines, file input and output streams, and data layer interfaces, while me engineered the synchronization primitive, mutex protocols, semaphore boundaries, and the starvation free fare ticket queue. I also built and executed all six test cases and validate the consistency within the log files. And finally, Azim and Hafi also compiled the report details, formatted the log analysis data, and managed the presentation slide production. That's all from us. Thank you.